Right, so I'm going to run the Euclidean algorithm forwards and backwards. So I'm going to start with 43. At least my numbers are smaller, right? So this is going to be 2 times 20 plus 3. And then I'm going to take, am I right so far? 20 goes in here 6 times into 3 with a remainder of 2. And then I take 3, and it goes in 1 factor of 2 with a remainder of 1. Okay, so there's the answer. We get a 1 there. And now, what we want to do now is actually run the algorithm backwards. So not just forward, but also backwards. It's only 3 steps here. It's usually not very many steps. But just try and do it carefully. So going backwards, 1 is equal to 3 minus 2. I then substitute in what 2 was, which is 20 minus 6 times 3. And I simplify that before I go any further. So this is going to be 7 factors of 3 minus 20. Okay. And now I take the 3, which is the next smallest number on the chart here, and write it as 43 minus 2 times 20, and then minus 20. So that gives me 7 times 43 minus 15 times 20. Now, if you have time, it never hurts to check that. I think that, you could make a mistake, and it'd be nice to know that. Depends on how much time you have. If you don't have a lot of time, maybe you don't want to spend too much time on that. The point, though, is that in mod 43, what this equation tells us is that negative 15 times 20 is congruent to 1 mod 43. So our magic inverse for 20 is negative 15. Okay. So that's the thing we want to multiply by. So we're going to get, so I'm going to multiply through by negative 15 over there to get x congruent to negative 15 times 19. And this is all still modulo 43. And let's see, negative 15 times 19 is negative 285 mod 43. All right, so are we done? Definitely not. That's a solution mod 43. So this actually represents many solutions. So what do you suggest that I should do at this point with this? Sorry? Yeah, get an answer that's between 0 and 42. Okay, so we would like to get a positive, like sort of the smallest positive answer we can find. Okay, how are we going to do that, by the way? You know what I see people do all the time? I remember this from 6 years ago. So people take this number, they start adding 43 to it. Add 43, add 43, add 43, add 43, add 43. It's going to take a while. In this case, it doesn't take that long. A better approach would be to just figure out how many multiples of 43 do I expect to be able to lop off. And then that will quickly elevate you to the right answer. You have to do division instead of addition, and I apologize for that, but it's very doable. So this is about 6 times that it goes in there, right? So if I do that, this is 258, so the remainder is 27. Okay, so negative 285 is the same as negative 27. And negative 27, of course, so you asked, Brittany suggested we get a positive number, so that would be 16. If we take 43, subtract 27, and change the sign, it's positive 16. Okay, so so there you go. This actually represents all solutions to that original congruence, right? So how am I going to get we have to be careful, find the 3 smallest positive solutions. So what am I going to do? Start with this one, right? 16, and I'm going to add 43 to it. Add 43 to it, we get 59. And then add 43 to it again to get another one, which is going to be, I think, 102. Okay? Now these are all congruent solutions in the world of mod 43, right? But as soon as I go back to mod 301, of course, they're not congruent anymore. I mean, I wanted 3 non-congruent solutions. So I'm getting 3 different answers for x in the world of mod 301. Actually, I'm not even thinking of these as in mod anything. I'm just thinking of these as integers. Which 3 smallest integers can plug into that equation and work? And so this would be that. Again, if you have extra time to check your answers, it doesn't hurt to do that. You know, you have to do a little bit of arithmetic though. Take 16, one of the choices. You could at least plug it into this one. 20 times 16, right? You could at least plug it into there and make sure it equals 19 in the world of mod 43. Okay, there we are now. So that's kind of an example of a little problem involving mods.
I have a question.
Yeah, go ahead.
So when we're working on mod 43 and we got 3 smallest solutions
Yeah.
for that, I mean those are congruent. But once we go to the bigger mod, they automatically become incongruent solutions.
Yeah, they're going to be incongruent. Now, if I had continued to make this list longer, right? If I go far enough along, keep adding 43 to the solutions, I'll eventually get after the 7th time. Notice, remember, we divided through by 7 up there. So the congruence in the world of mod 301 after every 7th time is going to be redundant again. I mean, so in other words, somewhere in your list, you're going to have a 317, I believe. If you were to keep adding 43 for a long time, you should end up getting that. And so this one now is congruent to this one again, right? So if the question had asked you to find 7 incongruent solutions to the congruence, mod 301, you would want to stop, you would want to write down these first 6 and then not write down anything after that. Okay? Let's try another few examples here. Number 4, right? Everybody doing okay so far? All right, here we go. So find, number 4, find 4 different integers. Find 4 different integers x with x congruent to 56 modulo 100 and 7x congruent to 32 mod 80. 4 different solutions here. It's kind of it's what we want to look for. Just a second to write that down. So this is a system of congruences. Can I apply so when I get systems of congruences, what sort of things do you usually think about? Chinese remainder theorem, can I use it? No, remember that the moduli have to be relatively prime pairwise. So you look right away, you see that these are not. And in fact, if the moduli are not pairwise relatively prime, then your system may actually not have any solutions. So, I mean, maybe this question should say, find 4 different integers x, if possible, you know, that satisfy this. Do you guys remember the condition for deciding whether one of these kinds of systems would even have a solution? It's really in the same section as the Chinese remainder theorem. I don't remember what the number is. It's actually these 2 GCDs, the GCD of these 2 numbers, I should say, has to divide the difference between these 2 numbers. However, there's a little catch here, which is that the second congruence is not in the right form yet, because there's a 7 in front of here. So that's actually also problematic right now. So this is actually a problem that has sort of several steps. Like the first thing you need to do actually is not even worry about the first congruence. You need to replace the second congruence with another congruence of the form x congruent to something. So let me just write down again. So if you have, we did this a couple weeks ago, if you have two different congruences like that, then in order for this to have a solution, the GCD, this will be in your notes, the GCD of m and n has to divide a minus b. That's the condition. And then you can find, at that point we went through a method to get the common solution. But see, I can't use this yet because the a and the b here, the a and the b here is not 56 and 32. Agreed? Does everybody follow that? Because the thing is, the 32 is what we have with the 7 in front of the x. So I need to figure out what is the x congruent to first. So I'm just going to focus only on the second equation. This is how you ask sort of two questions. Because we're going to do another linear congruence right here, first of all, and then we're going to have to go back to the system again. And actually, who knows, maybe we'll get stuck just even on this part. I mean, if the second equation has no solutions, then this whole system definitely has no solution, right? So this is kind of a repeat of what we had just gone over with the other problem. You look at the GCD of 7 and 80, which actually turns out to just be 1. And then as long as that divides 32, there will be a solution. It does. And then you just have to figure out how to find that solution. So let's do this very quickly. The numbers here are not too big, so I think we can do it really quickly. 80 goes into 7 goes into 80 11 times with a remainder of 3. And then 7 and 3, we take 3 times 2 and add 1. So it's actually very quick, just 2 quick steps. So 1 is equal to 7 minus 2 times 3, and 3 is 80 minus 11 times 7. And now we simplify that, and we get, what is it, 23 times 7 minus 2 times 80. Okay, did I do that too fast? It actually works. I can check it. 161 minus 160. So I must have done it right. And so therefore, 1 is congruent to 23 times 7 in the world of mod 80. So we just multiply through by 23 on the second congruence. Okay, so I need to figure out 32 times 23 without a calculator. $736. Okay, so we get x is congruent to 736 modulo 80. Let's just subtract 800 from 736 because in the world of mod 80, 800 is 0. Okay, feel free to use these kind of tricks. You know, very easy to come up with that. It's just going to be negative 64 mod 80, and then you can go back and add 80 to that again if you want to get a positive answer, which would be 16. Okay, so now let me just make sure I did that correctly. I did. Good. Okay, so now we have a new system. We're basically going to replace this second equation with a new equation. So we have a new system when we write it here. X congruent to 56 mod 80 and x congruent, I'm sorry, mod 100. Sorry, x congruent to 56 mod 100 and x congruent to 16 mod 80. And then we now can use our condition over here. So I need to take the GCD of 180. Anybody tell me what that's going to be? It's actually 20. Okay, so it's 20. And does 20 divide the difference of 56 and 16?
Yes.
Yes, it does. So that means that there is going to be a solution. This is possible. So 20 divides 56 minus 16 implies this has a solution. Okay, so that's good. And the solution that you get, so such solution is unique modulo, do you remember what? Exactly, the least common multiple of 180. What is the least common multiple of 180? I'm just going to use this. So I take A times B. So does everybody have our 400 is the answer? So it's 100 times 80 divided by 20. Sounds like 400. Okay, good. So this is a unique solution modulo 400. Okay. So we have that, and so we're not going to use the CRT, but what we can do is write A minus B, 56 minus 16, as a multiple of the GCD. So that's really what we need to do. So 56 minus 16. What I'm doing right now, guys, is actually deriving the solution. So far, all I did was I replaced the old system with a better system. I checked that it did have a solution. Now I'm actually finding it. So I'm reminding you how that works, right? So the way it works is you take the A minus B. You know that it's a multiple of the GCD, otherwise you would have stopped and said there's no solution. So there has to be a solution, and you just simply take 2 times 20 in this case. All right, and then the 20, okay, of course we also know that 20 is expressible as a linear combination of 180, right, of those two numbers. And actually it's obvious in this case what it is. I know how to write 20 in terms of 80 and 100. It's simply subtraction. Okay, let's say you're on another problem somewhere and you don't really see what's going on there. It's not a problem. All you do is you just actually do your Euclidean algorithm again on this one, right? So I see some people nervous, like, oh my gosh, what if I can't do that? See, here it's easy. You can just see that 20 is 100 minus 80. But if you don't see it, then just do the Euclidean algorithm. I'll just put it right here. Oh, there you go. There's your one step of your Euclidean algorithm. Your GCD is right here, right? So run the Euclidean algorithm backwards. Now running it backwards just means solving for 20, and we get 100 minus 80, which is actually what you want to put right here as well. So you just simply put that in there. Okay, so 56 minus 16 is 2 times the quantity, 100 minus 80. Are we good so far? All right, and then okay, so let's actually multiply this out. So this is 2 times 100 minus 2 times 80. What we need to do is basically rearrange the equation so that let's see. Yeah, so I'm going to rearrange the equation so that the 56 and the 100 are together, and on one side, and the 16 and the 80 are together on the other side. So basically the way that would look, so I'm going to rearrange. You'll see why in a second. If you haven't appreciated this before, you'll see what's going on. Basically, I'm going to rewrite this as 56 minus 2 times 100 is equal to 16 minus 2 times 80. Now, this number, whatever it is, and I'll just tell you right now, it's negative 144. But this number, whatever it is, right, I claim satisfies both equations. So plug it into the mod 100 equation. And I'm going to plug this one into the mod 100 equation. I'm going to get, yep, it's 56. Right? So this number, would everybody agree that this number is congruent? If I think of this as my x, this number is congruent to 56 modulo 100. Right? And would everybody agree that this same number, see there's an equal sign here, so it's the same number, and you can all do the math, it's still negative 144. This same number, when plugged into the second congruence, works as well, because this number is congruent to 16 modulo 80. You see, it makes both equations true, right? But to see that it makes both equations true, you need to appreciate the equality of the two different ways of expressing the number. This way of expressing the number shows me that it's congruent to 56 mod 100. This way of expressing the equation shows me that it's congruent to 16 modulo 80. Okay? So the way that you really want to deal with something like this, the trick here to this is to put the two numbers that are in the same equation on the same side of the equation. So when you did this expression of A minus B in terms of the GCD, you eventually get this equation, but you need to rearrange it. I'm just trying to make sure everybody rearranges it correctly. You need to rearrange it so that the numbers in a particular congruence are together on the same side, so that when you then reduce modulo that, you know, for example, the left side, you reduce modulo 100, you get the 56, which is what you want, right? But then when you reduce modulo 80, you have to think about it from the right-hand side perspective, and the 80 goes away, and you get the 16. So the answer then, is everybody with me? All good? Not too bad, really. I mean, really not that much work on the board here. It's a very short bit of work. Yeah, Jeff?
After we got the x congruent to 16 mod 80,
Yeah.
if we saw it by inspection, would that be okay? Or would we need to?
You're going to make me make the numbers bigger and bigger, aren't you?
Well, if 180 make it really simple to do it by inspection.
A 180?
Or the mod 100 and the mod 80 make it, to me, very simple by inspection.
Because, okay, so you can take,
Could you say 240?
because you can take a number and add 100 to it.
Well, basically, you figure out when is a multiple of 80 more than 40 more than a multiple of 100. And so it's 240 and 200, so you know it's 256.
Say that one more time.
When is a multiple of 80 40 more than a multiple of 100? And that's at 240 and 200. So if it's 16, then you know it's 256.
Okay, so you may or may not recognize that.
I mean, but if we had that situation, if I explained that part, would that be okay?
Maybe you should ask me if it comes up, okay? I'm not gonna, I don't think it's gonna come up. This problem has relatively nice numbers because the 100 and the 80 are very, very, very nice. But yeah, I agree, sometimes by inspection you can sort these things out. I'm usually not real happy with inspection, and that's usually my fault because I wrote a question that a person could do by inspection. But yeah, I would prefer to see the details of it. So anyway, this number, this common number here is negative 144. Did you see that in your head too, Jeff? Okay.
Subtract 400, mod 400.
All right, negative 144. Okay, so that is a solution, and it's and it's unique. Unique modulo 400. So it says find 4 different integers x that work, right? So what other x's are you going to put in here? It doesn't say that here. Just 4 different integers. Okay, not this problem. Just this. You can add and subtract 400 all you like, and you know you have another solution. And if you don't add or subtract something that's a multiple of 400, you will not have a solution because there's a unique solution modulo 400. So I would just add or subtract 400 all day long, and just to make it easy on myself, plus I don't want to get Jeff's answer, I'll just add 400 like that. And there you go. Okay, so that would be 4. There, of course, would be many other right answers. You could give me any 4 answers that work, and I'd be happy with that. I just add 400. The solution is unique modulo 400, which means modulo 400, these are all the same, right? So they all work in both equations. I mean, think about it. Your equations are mod 100 and mod 80, so if you start adding and subtracting anything that's a multiple of both of them, you're really adding and subtracting nothing. But of course, it's going to work. That thing's still rolling? I guess it is.
I don't know.
It is.
It is, okay. Great. Okay, we all good on that? Yeah, Larry.
Where did we get mod 400 again?
It's the LCM of, so the theorem about these congruences, these systems of congruences, is that there will be a solution if the GCD of the mods divides A minus B, and that solution will be unique modulo the LCM. So the LCM, I just used this equation and said LCM is just gonna be, 100 times 80 divided by 20 here, right? LCM there, so you just solve that out.
Okay, thanks.
Yeah, sure. Okay, let's try another problem. I'll do maybe one more computational one for now, and then we'll go back to theory. We're going to do a little bit of back and forth on all of these. Okay, so come back over here. Can I erase on this side? Stephanie, are you good? Yeah. Okay. Everybody else good? I'm checking the looks on your faces. Guys, the idea, and I said this to my 250D class when I did a review session last week, the idea is you don't walk out of the review session saying, oh yeah, now I know everything. The idea is, this is sort of where you're finding out what are you strong on and what are you not so strong on, so that you can now, hopefully in the next 2 days, figure out where you need to put a focus in your study. That's the purpose of it. I don't want you to think of this as like a checklist, like, oh, I checked off doing the review session, so now I'm good. Right, so don't feel bad if you leave feeling like, oh my gosh, I don't know how to solve systems of congruences, with the mods or not. That actually means that you were good to come here and see this and remind yourself that you need to practice it some more. And you have time to. The reason I chose Saturday over Sunday is you have more time to go sort out some of the issues that you're unclear about before you have to take the test. So that's the reason. Okay, so what number am I on? 5? 5. Okay, good. Okay, so here we go. We're going to have a new. This is a word problem, so I'm going to abbreviate the words a little bit. We're going to have a new scoring system for basketball. And what it's going to be is field goals are worth 4, 6, or 9 points, depending on where the shot was from. And in the last game, my team made 23 field goals. My team made 23 field goals and scored 137 points. Okay, so here's the problem now. So that's the information. And the problem is make a list of possibilities for how many field goals, almost done with this. Make a list of possibilities for how many field goals my team made of each type. So there's 3 types of field goals: 4 points, 6 points, or 9 points. This is a new scoring system, and that's the given information. Okay, just a word problem to sort of start us off. Okay. So any suggestions as to how to sort of start this thing, get this thing rolling?
We can write 2 different equations. We can write.
Maybe before we write down any equations, let's think about what kind of variables. Yeah, I like your idea, but I just want to go slow. So what kind of variables would we want to introduce to this? Chris?
We're going to be using integers